All right, thanks for joining us, everyone. Welcome to the California Advanced Homes Program webinar on the 2016 Residential Code Changes. If you have a question, please enter it in the questions bar on the panel on the side of your screen. We will pause periodically to take questions throughout the presentation and again at the end. The presentation is being recorded, and we will send you a link to the recording as well as the slide deck later this week. My name is Allison Whitwer, and I am on the CAHP program team. My colleagues and I work for TRC, and we implement the program on behalf of PG&E. Any inquiries or correspondences with the program will be with us, but PG&E is the source of the incentives and the vision behind the program. Before I send the presentation over to Scott, I would like to launch a few polls. So we'll start by finding out who is in our audience. If you can take a moment to make your selection. Okay, just a couple seconds more. Okay. So it looks like the majority of our attendees are energy consultants. We have some HERS raters, architects, utility representatives and building officials, and maybe a contractor or two. Our next poll is just trying to find out what other programs you have participated in before. We have single-family new construction, multifamily new construction, or none of the above. And you can select multiple if you've participated in both before. Okay. So mostly we have single-family new construction, some multifamily, and some of our attendees have not participated before. So glad you joined us so you can find out more on that. And lastly, we just kind of want to see what you're hoping to learn today. You can select more than one, so it's either single-family code changes, multifamily code changes, non-residential, high-rise residential, or just code in general. I'll give you a little longer to reply to this one since they're a little more in detail. All right. So mostly people would like to learn about single-family code changes and just code in general with some multifamily, non-residential, and high-rise residential as well. Okay, so our speaker today is Scott Blunk. He is the program manager for CAHP and CMF&H. Scott has been in this industry for 15 years. He worked as a contractor, HERS rater, energy consultant, and an engineer before working on program implementation. So I'll let you take the wheel, Scott.
All right. Thank you very much, Allison. And we'll go through, oops, there we go. So do you want to go through this, Allison?
Yeah, I kind of went over it earlier, so this is where you'll ask a question.
Okay. All right. So I am the program manager for CAHP and CMF&H. CAHP is the California Advanced Homes Programs for the Single-Family New Construction Program. CMF&H is the Multifamily New Construction Program. CAHP is for 2017 will be run in PG&E service territory, SoCalGas, and SDG&E territory. SCE is not participating this year. The point of the program is really a market transformation program, more so than an energy savings program. The point of the program now is to work toward the more stringent requirements that are coming into the code, as well to talk about in a bit, and for 2016. And then also moving builders beyond 2016 and just being able to implement it into the 2019 code and beyond that. And we do that through trying to structure incentives, financial incentives, through design assistance, and a lot of different avenues. We, the program is funded under the auspice of the CPUC, and we welcome that. So the program requirements are listed here as a little bit vague on purpose, but essentially for 2017, the the home for CAHP, since this is sponsored by CAHP, must be permitted to the 2016 Title 24 standards. Um, PG must receive PG&E territory, although CAHP is available in other service territories. Be new construction, single family or duplex townhome is considered in this, or is used in this program, and then they have to meet certain energy performance requirements. The uh, the the program is changing, is probably changing slightly, and that change will be announced in the next few weeks. But we're looking at a slightly different program structure that will allow a more equitable entry across the state. More information will be coming on that, so stay tuned. And the energy consultants listed on the projects must be a CEA under either the 2013 or the 2016 code. At some point, we'll drop to 2013, but we have it for now, just to make it easier. Okay, so to talk about, so today we're going to talk code changes, really, but I really love to start out with some context for the code change and just kind of how we got here in a little bit. So sometimes I realize we can all be kind of muddled through our day and our week, and we forget really the amazing achievements I think that we've done in the past and what the code has been able to shape. So this may be all well known for everyone, but I think it helps shed some light on where we're going, looking at where we've been. So the CEC started in 1975. That's the black line on the graph, and the vertical line. And you know, it's just what was happening back then, and the turmoil in the country back then was, you know, Watergate had just we just went through that. That was impeachment of our president. 10% inflation, which is something we haven't known for the last decade, if not generation. OPEC, there was oil shortages, there was lines to get gas. So there was a global recession. Vietnam War had just ended. There was a lot of fear about security and particularly energy security. So that's some of what was going on and what got it started for the CEC. And the blue line and the red line, the blue line is the per person electric consumption in California. The red line is the rest of the country. And I think it tells a huge story, and it tells a huge story about what we've been able to achieve as the state of California. That in the last 40 years, 42 years, or this graph maybe 40 years, let's just say, we have not increased the amount of electricity we use on a per person basis. Which maybe doesn't sound so great, except for the fact of, you know, 40 years ago, the internet didn't exist. Computers certainly didn't exist in our pocket and in our home and on our walls at home. Air conditioning existed, but certainly not in every home, very few homes back then. So we've added a ton of electronic devices to our lives since then, and yet through our efficiency standards, we've been able to at least not increase the amount of electricity consumed. So I think it's a real pat on the back for what we all as an industry have been able to accomplish. Where the rest of the country, as you can see, they've been drifting up.
Hey, Scott.
Yep.
We have a couple people saying it's kind of hard to hear you. If you can try and speak a little louder or move your headset a little closer.
All right, will do.
Thank you.
Thank you for that.
Mm-hmm.
All right, I'll try to talk louder. Okay, So that the impact of the building standards over the last 40, those same about roughly 40 years is shown here, and just the water heating, the energy use for water heating, space cooling, and space heating, and it just shows the really dramatic drop off in energy use. And it also, I mean, what you also see is there in 2016, 2019, there's just not a lot more we can do, and that's certainly will be coming out in the code and is in the code that it's becoming more and more difficult to get savings. So the code is kind of shifting from an energy efficiency code to a grid harmonization code. And there's another webinar on that in a couple of weeks of what that's going to look like, what grid harmonization really looks like in terms of the CEC. So I think also to understand code, I think understanding what the CEC calls Z&E is important. And there's a lot of different definitions of Z&E. Whether I think the layman on the street would think that Z&E, zero net energy, means that they don't have an electric bill, and that's represented on this slide as a zero net energy cost. The other one that probably most people would think would be a zero net site energy, so that's on your bill, your therms and kilowatt hours. And there's other definitions, and some people like these definitions over others, whether it's zero source or zero emissions. But the one the CEC has adopted is the zero net TDV energy. And TDV is also very important to understanding the code and how to make buildings more energy efficient. And I'm not going to go into it, but TDV, time-dependent valuation, it's just giving a value for the amount of energy you used based on that time of the day that it's used. And I'll show you a little graph about that. Now, the interesting thing, this is an older slide, and what used to be called TDVs is zero net TDV energy, time-dependent valuation. In the last 2 months, it seems as if the CEC has changed the definition of Z&E to be zero net electric consumption, site consumption. So again, we'll talk about that in a couple of weeks. So the definition of Z&E is shifting a little bit, and I guess maybe dramatically, but it is changing. But 2016 code, that was the zero net TDV energy was the definition at the time that was put together. So also understanding the code is understanding where the energy is coming from. So solar has been thought to be, certainly outside the energy efficiency industry. Everyone thinks, oh, just put solar on it. We don't need efficiency. And this graph is just showing the yellow line is showing the energy created by solar by the utility company. So this does not include what's put onto the grid or what's put onto the grid by solar on rooftops. The blue is wind, and wind is very variable too. This was a screenshot out of something that you can look at it live every day. But this was taken a couple months ago during that last really severe winter storm. Just showing the levels, and this was the next day, and the storm was kind of blowing by, and you can see the wind being generated is slowly decreasing. Wind on a typical day is very small, between 200 and 400 megawatts, but this is again in the winter time, so that yellow spike hump in the middle of the day where the solar electric is being generated on a sunny day is much, much greater. And this is 9% more solar just in one day, but month over month it can be highly variable. And why this matters so much is this, and this is kind of a real-time duck curve, and this was done in early January. But the blue line, the solid blue line, and the dotted blue line is just a forecast. The solid blue line is the actually what was the demand on the grid, and the green line is the demand on the grid if you take away well, renewables, but solar is the main one that's causing this big dive in the middle of the day, because our energy demand throughout the day doesn't really fall like that. And every day is this shape of this graph looks a little bit different, but it's in generally the same. Your peak's going to be higher in the summer, and it's going to be even more dramatic. But uh, and why I say this in a code change is because I think it's great context. What the real issue is that time on this page between 1400, that's 2 o'clock, right, military time, to 1800, so 2 to 6 p.m., the huge acceleration or the ramp up in the green line that's being seen, that's really the sun is setting, so that energy that's being demanded by the grid has to come from non-renewable resources. So this is really power plants are being fired up at that time and coming online, and it's the rate of that acceleration or that rate of deployment of utilities, of power generation stations. That rate of acceleration is the real struggle of the grid, and because PV solar PV in itself can't be stored without something else, and gets back to the grid harmonization. So saving energy from this on this chart 2 to 6 p.m. is kind of one of the more critical areas to save energy, and we have to do it in more than just efficiency. And I guess this is the renewable energy breakdown, but I want to pause for a second to see if there's any questions.
Not yet, Scott.
Okay. All right,
Thanks.
we'll keep going. So the renewable energy breakdown, there's a lot of ones out there. This was updated in December of 2016, so it's very fresh. But right now the grid, there's about 28% renewables on the grid, and this is the renewables owned by the utility companies. It does not account for any renewables on our rooftops. So it's total energy is greater, but from what you've seen on the previous slides, the more renewables, the more PV that goes on the grid, the higher the ramp up, and it causes other problems. All right, so also understanding how to make buildings more energy efficient. It's super important to understand the climate zone you're working in, and I think this goes without saying, but I've also seen so many times where people forget what climate zone they're in, or just don't understand the differences. And as an energy consultant, wearing an energy consultant's hat, like that's our job, right? To really help people understand the differences in climate zone to climate zone. And some of I've seen it many times where somebody in like climate zone 7, so that's coastal San Diego climate zone, the contractor, let's just say, thought it was a great idea to put a cool roof on because cool roofs save energy, right? Well, cool roofs save cooling energy, and if you're in a climate zone that has heating energy and no cooling energy, then it increases. Putting a cool roof on increases the energy used in the building. I've seen that a lot. I've seen climate zone 3 where people put high solar heat gain coefficient windows because they couldn't wait on the energy consultant, and they just put in better windows. And what is a better window? Well, that all depends on the climate zone you're in. So climate zone 3 along the coast, and not every, and climate zone 3 along the coast, you just got to be aware that like solar heat gain through your windows can help reduce the energy consumption. And so there's a lot of practices like that in where you just need to be aware of the climate zone, and solutions in one climate zone are not the same solutions in the next climate zone. And then this is under the 2013 code. We haven't updated this for the 2016 yet, but this is per climate zone energy use in residential and where we're seeing that energy being used. And this points out what you should know if you understand the climate zones. And so some examples, 6 and 7 are the southern coast from about Tijuana to San Luis Obispo, about there, right? So what you've got is virtually no space cooling, a tiny bit of space heating here in 7. 6 is pretty close. Green is the water heating, and the rest of this is plug loads. And you'll notice in almost all these climate zones, except for these ones up here, plug loads is a really big part of the energy use in the buildings. And it's not plug loads, let's just call it non-regulated loads. That can be lighting as well. So that non-regulated loads is a much larger piece of the puzzle of energy use in buildings and will be emphasized more in future codes. Some other climate zones, so 15 is the very southeastern corner of California, the desert next to Arizona, so tons of cooling energy, no heating, and virtually the same unregulated loads. 16 is like in the mountains, Tahoe, lots of heating, virtually no cooling. So just again, it helps you understand if you're designing or developing a building in a climate zone where you want to spend your money and time. What sort of energy do you want to save? Is it heating? Is it cooling? Is it water heating? Where else can you save energy? And then maybe this doesn't apply to a presentation on the building codes, but I believe that there's so much more energy to be saved in a building and how you operate it, and that's really the energy conservation piece. The energy efficiency piece really talks about the code, and then there's the renewable. But I won't go into that too much more. So we'll pause again if there's any questions on that before we go.
We did have a question from 2 slides ago,
Okay.
asking if the slide was referring to a gas hybrid house or an all-electric house set to TDV values with gas not available.
This is set to a gas heating, electric cooling. Yeah, so the gas electric combo house. That's what you see typically across the state.
All right. No other questions right now.
Okay. All right. So changes to the code. Sorry. Major changes to 2013 code that make it the 2016 code is kind of how this should be read. But ductwork was a really big emphasis in this code, and ductwork is such an emphasis on this code that they attacked it via way of the attic. So the changes to the attic are really all about trying to reduce the amount of energy lost through the ductwork. So there's a lot of changes in the code on attics and putting in high performance attics, but that's all about really saving energy in the ductwork. And then there's walls. Walls got bigger and thicker. Whole house fans, really some small minor changes, but I think it warrants some discussion just to bring it back up to everyone's attention. And then lighting got easier, I think much easier to comply with, and we'll go into that. The code is made up of, these are all the different pieces of the code. There's a lot of about 2,600 pages of code here, and someone brought it up to my attention the other day that I thought was something interesting that I hadn't thought much of is, the energy code, those 2,600 pages, they have some fairly major changes in them every 3 years. And that's why we're doing this webinar, right? But the plumbing code and the structural code and the other pieces of the building code are fairly static code cycle to code cycle. So we're the lucky ones that get to really learn new standards every few years, every about 3 years as the code changes. It's an interesting piece. And over the year, this is where we've gone. So the efficiency increases code cycle over code cycle. If you add those up, I do believe, well, they're almost 100%, 60, 90, yeah, 95% or so, almost 100%. But what that's really saying is obviously we can't save 100%, but we're getting to the end of our rope, which is what we've demonstrated in some previous slides. The 2016 code is theoretically about 28% more energy efficient, and the 2019 code it's looking like it's going to be about 15% more energy efficient. It's too early to really know, but all of these are estimates because it's based off of kind of a statewide average. So no building necessarily is for 2016 28% more efficient, but that's going to be kind of the statewide average. So in the standards, the efficiency standards contain parts for newly constructed buildings and additions and alterations have to do with energy efficiency standards, water efficiency, and indoor air quality. Although the energy efficiency piece of this 289 pages is by and large the majority of everything that's made up in this book. Water is just too cheap, and indoor air quality is just a smaller piece of this book as well. So the standards are divided into 3 different parts. There's the mandatory requirements, which is the absolute bare minimum what you can do. So an example would be like R13 in your walls. You can't do less than R13. Then there's the prescriptive packages, which is in the code, in previous cycles in the code, the prescriptive packages have been all about how to build a building without running an energy model. That's not true anymore. You can't building a building prescriptively is really not possible, although I'm sure somebody will tell me that it is. But on all practical reality, you have to do an energy model every time. But what the prescriptive packages does is it sets the standard home or the baseline or the energy budget. The prescriptive, if you're building a home, the modeling software will build the same home or the same building at the same geographic location, at the same orientation, and the same square footage. This software is building this one in the background, and it's just, but it's building it with the prescriptive package involved. So that's really the majority of the changes in the code are all the prescriptive packages and what's changed. The performance standards, the performance method here then compares your software showing your home and how it compares to that prescriptively built home in the software. And then it compares whether you're using more or less than that energy budget that was created in the prescriptive package. So this was put out by the CEC and just explains all the code changes in one page. The new piece on here is that the estimates from the CEC says that the average new home will increase in cost by $2,700, and that'll result in $7,400 in savings for a 30-year mortgage. And this is the government looking farther than we typically do. They're looking 30 years out of the life of this payback, where uh, worked for a lot of building owners, and they usually want 2 to 3 year payback. So, but the code is looking much farther than that. All right, so ductwork. Really, the mandatory requirement for ducts is all ducts in conditioned space have to be greater than or equal to 4.2. And the leakage requirement has went from less than 6% to less than 5%. In reality, this is a really pretty minor change, although it will, I'm sure there'll be times when it causes heartache to people trying to get their ducts to pass. But 5% is quite doable. I believe, and I know people who install ducts every day that can get much less leakage than this. And when you look at it in terms of leakage and what that does to the house, I mean, it's pretty direct correlation that if you're leaking 5%, that means 5% of the money you spend to heat and cool the house is leaking out before you get any of the benefits of that. So kind of you're taking a 5% haircut right off the top at a 5% leakage rate. So that's still a lot, I think, but very manageable change. So like I said, a lot of work in the attics on this code change, and they're trying to fix the attic to help fix the issue with the ducts, the duct leakage. And why do we put ducts in the attic, right? Why do we do that as an industry? It's the worst place to put them. It's the harshest environment in most climate zones of California anyway. It's the harshest environment. But it's simply easy and inexpensive to put them in the attic. So cheap and easy. And that's how, a lot of our building customs have evolved anyway, is we do what's cheap and easy. And, frankly, the architects don't pay a lot of attention to how ducts are installed in general. And so they just kind of assume that the attic's a nice big wide open spot, just figure out where the ducts go in the attic. So less design work for them inside the conditioned envelope. But so the code objective here is to lessen the harsh environment of the attic, and that's what we're doing in this 2016 code. And we're doing that we're insulating the roof, and that's insulating the roof in addition to the ceiling. We are adding cool roofs and radiant barriers. That's nothing new to the code, but it's all about trying to reduce the load on the ducts. And in general, the ventilation of the attics has not changed. The other way to address this is just to put the ducts in conditioned space. And putting the ducts in conditioned space is certainly the very best way for energy use. That's how the majority of multifamily units are built, with the ducts in conditioned space, a small drop ceiling in the hallway, and short ducts go into each room. But in single family, putting ducts in conditioned space can be problematic. It's just a design challenge. So the changes, there's 3 prescriptive options in the attic. High performance attic A, B, and C. And A and B is that insulating the roof deck. C is moving them into conditioned space. And then beyond those prescriptive, there's a couple other ways to reduce duct loss that we'll address. Sealing the attic and no ducts. So prescriptive option A is you will insulate the ceiling just like you normally would, whether it's either R38 or R30. You would install continuous roof deck insulation, and that's an R6 above the roof sheeting, or an R8 with no airspace. But R6 is usually going to have an airspace, so you're going to have an R6 with an airspace, and that's above the roof deck. This method is challenging for most builders that I've talked to anyway. How do you do an R6 above the roof deck, and it's going to be some sort of foam, rigid foam above the roof deck, and the challenge is how do you get that to work? There's if you've got a regular comp roof, then you're going to have to still have something to nail to. So above your OSB, you're going to have your rigid insulation, and then you're going to have some sort of OSB, something to nail to again. It's quite a challenge. You could do that all together as a SIP. Again, quite a challenge to our industry. If you're doing concrete tiles or like the barrel tile, where you can do a slip-in piece of foam underneath them. There's the product is called Wedge It that seems to address this issue fairly effectively. But with this option, you're also installing the radiant barrier per your climate zone. So the table at the bottom here just shows in what climate zones it's required, prescriptively required. So again, if it's a prescriptive option, that means you don't have to do it. It's not mandatory in the code, but this is how your energy budget is being created. So if you choose not to insulate the roof deck here in option A, B, or C, or A or B anyway, if you choose not to do it, that's still how your house will be compared to a house that did do this. So if you don't choose not to do it, that's the flexibility of the code in action. You've got to figure out how to make up that extra energy use somewhere else. But yes, this is it's a prescriptive requirement for the house that creates the budget, the prescriptive house in climate zones 4 and 8 through 16. So climate zones 1, 2, 3, 5, 6, and 7 are the climate zones right along the coast all the way down to California. So it's required prescriptively everywhere else. What this also has, just to be clear, what this also has is a vented attic. So the green line at the ceiling, you're still insulating this to your 30 or your 38. The blue line, you've got insulation above the roof deck to a 6 or an 8 level. But that space in there is still vented, just like it would be, just like it was in 2013. Let me pause there and see if there's any questions.
We did have one about the duct slide, asking about using insulated ducts.
About using insulated ducts. So I guess the question is not quite clear to me. The roof, the insulation on the ducts hasn't changed. The insulation requirements, other than the ducts in conditioned space. Certainly, more insulation on the ducts is better, but it doesn't change the prescriptive option A or B.
Okay. We have a couple comments, but I think you'll address them later, and if not, we can follow up individually.
Okay, sounds good.
Mm-hmm.
All right, option B. This is high performance attic option B. So this essentially the same as what I just showed in the previous slide, except for instead of the insulation being above the roof deck, it's below the roof deck. So now you've got, still at the ceiling level, you've got your R30 or 38 based on your climate zone. And then at the blue, at the roof sheeting, you're going to insulate underneath the roof deck to an R13, R18 with no airspace, but most of the time it's going to be an R13 with the airspace. Still, you're venting the attic just like normal. Radiant barrier would not work here typically because you need an airspace next to the radiant barrier. So very much the same as option A. I see option B as an easier path for most builders because it really requires very little change other than somebody going up and doing R13 underneath the roof deck. Not a fun job at all, but it can be done without changing anything in the building process. The home can pretty much be done and send somebody up with a roll of 13 and a staple gun. Uh, Totally lousy job, but it can be done that way with very little changes, with virtually no changes to the process of building. The one note, this is one of the ones that is increasing for 2019, so the insulation under the roof deck is getting greater. But for right now, the addition high performance option B is R13 under the roof deck. Yeah, and this is just helping keep the attic temperatures down during the day, and it's vented so that it can cool off at night. And hopefully, if you're really in a severe climate, you also have a whole house fan that will flush out the attic. So that's the other reason that you keep the attic vented, so that the whole house fan can cool the attic. So for prescriptive options A and B, high performance attics. So again, just kind of a summary. The ducts and air handlers still stay in the attic. The attic is vented as normal. You're either doing R6 plus a radiant barrier, R6 above and radiant barrier below the roof deck. You're going to use your cool roof prescriptively by your climate zone. Or same thing, ducts and air handler still in the attic, vented attic just as normal, insulation's below the roof deck at an R13 or level typically, and you can still use a cool roof. The high performance option using the R13 below the roof deck is the baseline for the modeling and for homes in the ACM.
I have a question that came in, Scott.
Okay.
I think it was from the last slide. Do these R values include thermal bridging with the framing members, or is it just the insulation level of the bat insulation?
Great question. Yeah, that's just the insulation level of the bat insulation. It doesn't include the whole roof assembly, which, yeah, yes, that's just interesting that this is the way it's displayed or talked about. But yes, this is just the insulation of the bat insulation.
Okay, thanks.
Mm-hmm. And then the best way to go about it is the way most multifamily is done, and that's just move the ducts and the air handler in the conditioned space. This is the best way that you will not be losing, or you will not be losing extra energy through the ducts or any of the equipment, because now you've got it inside the conditioned space. By far and away, this is the best way if you're going to use a ducted system. And if you're going to do that, then the attic, you don't need insulation in the attic, except for at the ceiling level, and that's going to be just prescriptively. You're going to have your radiant barrier installed in all the climate zones except for climate zone 1, which is the very north coast of California. So there's a lot of different design options for this, but it's somehow it's got to be dropped into the living space, and I'll show you a few. Just to note that cathedral ceilings and sealed or unventilated attics do not qualify under this path, and there's a big issue in the energy consulting industry, that why isn't an unventilated attic treated the same or better, or the same as being in conditioned space. And part of the reason you do get savings from it, but part of the reason is you can't then have a whole house fan work as well. But that's part of the loss. We'll talk about it a little bit more later. But yeah, putting the ducts in the house, there's a bunch of different design options, but more than anything, and I don't know that any of these, except for maybe the middle one and the drop ceiling soffit, which is kind of the way multifamily is done, I don't see these others as true options moving forward. Yeah, and it could be, but it's going to take a culture change in our industry to start designing differently.
Scott, a question about insulation. How does the insulation below the roof deck affect venting the attic?
Okay, yeah. So the insulation below or above the roof deck should not change how you vent the attic. So obviously you just wouldn't insulate over on top of the vents, but they're not changing the venting requirements. So your O'Hagan vents, your eyebrow vents would all be done just as you would normally do them, but you're just going to insulate where there's not a vent area. So no change to the venting.
Okay, thanks.
You're welcome. So the sealed attic is a popular choice, especially from a bunch of building scientists and building science-minded folks, just to insulate the attic. So that's moving the thermal barrier and the air barrier all the way up to the roof line. That means at the ceiling level, there's no need for any insulation at all, but your thermal barrier and your air barrier is being moved up to the roof deck. The nice advantage of this is that your equipment's now in a kind of in a unvented attic. The CEC doesn't call it conditioned space, but it's for most intent and purposes, it's a lot like conditioned space. You do get really good energy savings out of it, but it's not the same as it being in conditioned space. The insulation that you're putting in the roof deck would still be per climate zone, minimum 30 or 38. Yeah, the below roof deck rafters R13 should be taken out of there. Sorry about that. That's an error. But it's just sealing that space. So you're on this option, you're no longer venting that space. And one of the main downsides is that whole house fans don't work at that point, or the current designs of whole house fans don't work very well. And if you're going to insulate the attic, there's lots of different ways to do it. You can the fastest and easiest way to create a thermal barrier and an air barrier is just using spray foam below the roof deck. That will give you both of those in one application. It is expensive, and of course, when you're sealing the attic like this, you're adding surface area where heat will be passing through. So you're actually there's more surface area to heat transfer through than if you kept it at the ceiling. So there's that trade-off with now the ducts in a semi-conditioned space. You can do it with netting, wire bats. SIPs is a great way to go. Again, not very welcome in the traditional building industry. I've built with them before, and they're great, but I haven't seen it in the traditional building. And then some of this is spurring some innovation, and this is a product by Owens Corning. It's called box netting, where this is stapled to the roof rafter. It's like this picture here where it's stapled, and the box part of it, there's like a little sewn seam or tape seam here that tries to hang it like a box underneath. And what you're getting is this insulation area between the 2x4 and down, and that gives you the thermal break. So this is one way to really to get your 30 or 38 or even more insulation at the roof deck and stopping the thermal break. You could also do this if you want to ventilate the attic, but I haven't seen it that way. It's a lot of work if you're going to do it that way.
We had a question about option C.
Uh-huh.
Is the air handler and ducting in drop a semi-conditioned space, or is this considered conditioned space?
In this picture on the slide that's up now, this is considered in conditioned space. The important part here is that the ceiling right above this drop ceiling needs to be airtight. Your thermal barrier and your air barrier needs to be complete going above the drop ceiling area. So it's considered conditioned space. Considered conditioned space, yeah.
Okay. And someone brought up the QAI requirements. I know we didn't plan on addressing Hearst tests in this presentation. Um, would you be able to give a quick summary on the changes to QAI in the 2016 code, or do you want to follow up on that privately?
Let me follow up on that.
Okay, no problem.
Okay. All right. The other option, and this isn't really in the code, is just no ducts or even just doing fewer ducts. Um, Mini splits, hydronic PTACs are all ways of getting rid of ducts and therefore the duct loss. There's advantages and disadvantages to all of those. Mainly in mini splits is that they're derated by the software because they're derated by the Energy Commission. But I think at the very least, uh, I think it brings up the conversation, or should bring up the conversation, about why do we have so many ducts in our house? And now that our envelopes are becoming so good, do we really need a duct going to a bathroom that's 50 square feet, 50 square feet or 60 square feet? Like, do we need a duct going to every single room, or can we move air through our ventilation system that's going to even out the temperatures? Because every duct you can get out of you can not put in the house means there's less duct loss conductively through the duct itself. There's less air leakage possibilities, and there's less resistance on the fan. So I'm a little amazed sometimes. Like, my laundry room doesn't need to be the perfect temperature when I walk in and out of it. If there's no duct there and it's 3 degrees different than the rest of the house, like, that's okay, but it would mean much more long-term energy use and energy savings by getting rid of a few ducts in the house. Some simple, easy places to do it. All right, so moving on to walls. So the top line there shows the 2013 wall U factor of 0.065. In 2016, it went to 0.051. The difference between U value and R value is just the reciprocal. So right now, in all but climate zone 6 and 7, the U factor went to a 0.051, which is an R19.6, so close to an R20. And that is the assembly R value. It's not the insulation in the cavity. So that's the assembly R value. Climate zone 6 and 7 didn't change from the 2013 standards. This is another area that is increasing, becoming more stringent for 2019 code, or it's looking to be getting going there anyway. Um, and this is also one that I've heard pushback or concern from the builders of building walls that are this thick, basically, because getting R value in a wall, really the only way to do it is to make it thicker. And that affects a lot of their construction practices and setbacks and various. So if you're going to build a 0.051 wall, here's a bunch of different ways of doing it. So the U factor here, this is your framing size, your stud spacing, insulation in the cavity, exterior insulation, and then kind of the type of insulation you're going to be adding. But what you'll see in all of these is all of these have a continuous exterior insulation. And in some parts of the state, this is not unusual or new. And in some parts of the state, and for some builders, adding continuous exterior insulation is a big deal. And especially for those builders that are really clinging on to they still want to build with 2x4s. If you're building with a 2x4, now you have to have an R8 on the exterior of the building, which is going to be 2 inches of rigid insulation hanging off of the wall assembly. That's a lot. Again, I guess I want to stress that this requirement is a prescriptive requirement, so it's not a mandatory requirement. You don't have to build an R19.6 wall, but this is what your building will be judged against. So if you choose to skimp and have a smaller wall, you've got to make up for it somewhere else in the building. And the code is really running out. We're running out of room with the code to where else are we going to make this up? So walls and attics are something that a lot of people push back on, but it's really important that we as an industry evolve and learn how to do these so that it works for everyone in the field, the architects, everyone. Because adding exterior insulation is a challenge. I built a LEED Platinum home probably 10 years ago with a couple inches of rigid foam on the outside. That was the hardest part of the whole house, was trying to figure out the details of those 2 inches of foam. And that 2 inches of foam adds a lot of complexity in terms of weather sealing, keeping the water out of the wall. It adds complexity. Now your windows are now 2 inches farther out away from your wood, so they're cantilevered out. Your doors have an extra 2 inch, so the jambs have to be bigger. Where does your J box go for your front porch light? There's just a ton of consideration for the big builders. Now what this would look like is essentially every home in their subdivision is now 4 inches closer together, 2 inches for each house, and that can be troublesome in various other ways. And this insulation could be added to the inside of the house instead of the exterior. It doesn't have to be exterior insulation by code, but you have similar issues with bringing the insulation on the interior with door swings. Your cabinets no longer fit your kitchen. Bathrooms are now really getting small. So there's a lot of other issues. Haven't seen any in California built with interior insulation. Saw some in Washington, but down here we're going to have it on the exterior. Again, this is the prescriptive requirement. So that continuous exterior insulation can be done in a few different ways. There's 3 main types of exterior insulation: expanded polystyrene, extruded polystyrene, and polyisobutadiene. They each have different R values per inch, so you can, and price pretty much goes up as you go down the list as well. So you can have less thickness on the exterior wall by paying more money, but you can't get away from it. This table just shows this is from the reference appendix. This shows, and I just bring it to your attention because the reference appendix is part of the code, part of some of the code books, and it gives you lots of different options for building a .051 or better wall. So everything to the right of this yellow dot is better and can be built. This table, 16 on center, everything from this line down is 24 on center, framing type, and then added exterior insulation. So really what this is showing is that at least on this one page, if you're doing wood framing, you cannot get away from doing something on the exterior of continuous insulation. The best you can do is an R2, which would be a 1/2 inch if you're building your walls with 2x8s, which is pretty rare. There are, of course, other ways to build walls. You can do a double wall here on the left, or a staggered stud wall. Both of those are options. And that essentially moves that continuous exterior insulation into the middle of the wall. It's giving you the thermal break that the exterior insulation does, but it gives it to you in a different manner. Probably not very practical for most homes. We see these in multifamily a little more, but probably not going to see them often in the field. And then we can just throw away the studs altogether and do a different type of wall assembly. Again, probably won't be very popular. I built with the SIPs, and that's a way to do it. Your walls are still going to be thicker than what we're used to, uh, but maybe it's time to rethink how we build walls, whether doing a SIP or structural insulated panel or an insulated concrete form, or maybe there's something else. So I say all this about walls and attics, and it's with a heavy heart that for full disclosure, I have to tell you that for 2016 code, you don't have to do walls or attics. You could just throw some PV on it, and you get energy conservation credit by putting an energy generator on your roof. It totally goes against my grain, what I've worked for forever, but this was let into the code. Basically, as I understand it, the concern of the builders were we can't build those types of walls and attics. It's too disruptive. It's too expensive. We don't have people that know how to do them. That was the concern. So this was put into the code that says if you don't want to do walls and attics, you can put a PV system on your roof, at least 2 or more kilowatt DC in a single family, 1 for multifamily. As long as you put 2 or more kilowatts DC on your roof, you will get the same energy conservation credit as if you did walls and attics. So you could do walls and attics and a panel, and you could double dip on that energy conservation credit. But this is an option for 2016. As I understand it, this is, the CEC is saying this is coming out in 2019. This will go away. So they're giving the industry 3 years to figure out how to build walls and attics and giving them this easy out. I would say with the easy out, it will make them not learn walls and attics. So, but for right now in 2019, this PV compliance credit is gone in 2019. Of course, part of the industry is fighting to keep it in. Part of the industry is fighting to take it out, but it's there right now. And just even though this shows up in the energy budget as energy conservation, it is not energy conservation, and it will not be treated as such in any of the new construction programs, CMF&H, CAHP. Neither one of those will allow this as an energy efficiency credit.
Quick question, Scott.
Good. Yep.
Do you still have to use a radiant barrier with the PV compliance method?
Yeah, it's still based on the climate zone.
Okay.
You would do a radiant barrier based on the climate zone. So that's 2 through 16. And that may be counterintuitive, but that's just the way it's put in right now. Any other questions?
Not right now.
Okay. So moving on to water heating. Moving on to water heating. So water heating, seems like I missed a slide here, but in water heating, basically the standard design water heater changed from a 0.6 energy factor tank water heater to a 0.82 energy factor tankless water heater. So tankless is now your base case, option 1. There are 2 other prescriptive options, 55 or less, 0.6, with QII in the walls, pipe insulation or compact water design, or option 3 is a larger water heater, 0.76, pipe insulation, compact water design. But the base water heaters went from a 0.6 storage to a 0.82 tankless. This is one of those where I think in the 2013 code especially, a lot of builders were taking compliance credit off of this one, and they still will, right? This is some federal preemption going on here, and it's an easy one to be more efficient than the 0.82. Also new, is just isolation valves are required on both the hot and cold for on-demand water heaters or instantaneous water heaters. And that's just so that they can be cleaned out. Moving on to whole house fans. Whole house fans, not a lot has really changed. They reduce the flow rate from 2 CFM per square foot of conditioned floor area of the house to 1.5, so the fans are a little bit smaller. The attic ventilation also reduced from 1 to 1 square foot per 750 CFM of airflow. Now, just a note, this is not ventilation, this is cooling. Whole house fans are about cooling the house or the building. It's not about providing ventilation, fresh, clean air to the occupants. Whole building ventilation system is a different system than a whole house fan. And the whole house fans are really the two pictures on the one on the right and the one on the left, different sizes. They move vastly different amounts of air, but they would be for a different size house. These whole house fans are probably the best way to save energy in the Central Valley. I would say anywhere from Fresno up through Redding, but the sweet spot is certainly climate zone 12 right around Sacramento. Whole house fans can save an enormous amount of energy, and because what you're doing is you're turning off the compressor, which is in your air conditioning. That's what uses all the energy. The whole house fan is a great energy saver. It's in the code. If you choose not to put a whole house fan in, it's a fairly large penalty, compliance penalty in the house. If it's a climate zone, the whole house fans work well in. So I would recommend, like, don't forget about them. Use them. They just don't work if you've got a sealed attic. But great. The middle one is the middle picture is a picture of a smart called a smart vent, or there's another name, night breeze. This really works on a single family a lot like an economizer does for commercial, and that's just where it senses outdoor temperature is lower than your set temperature inside on your thermostat. It's just going to turn off the compressor and bring cooler air in from outside. It's not as effective at cooling your house. It's usually the blower motor uses more energy, and I know I'll get at least one person complaining that these are, can be shown as being even better. I've had both, and I've had good luck with whole house fans. I guess I'll leave it at that. But it doesn't necessarily qualify as a whole house fan per the code, but it is another option out there.
Scott, I have a question. Does the whole house fan requirement also apply to multifamily 3 stories?
I do not believe it's part of the base case in multifamily, the prescriptive option in multifamily. It certainly could still be used, and you could get compliance credit for it. It would be challenging, though, to use it because it really requires an attic area and ducts in unconditioned space. So it's not going to be, it's not going to be a prescriptive option in multifamily. Could be used, but it would look very different, I think.
Okay, thanks.
All right, lighting. I mean, this is the one that I think is kind of the coolest, the lighting changes. And I think it's cool for a lot of reasons. So what this slide is showing you is the lighting guide for 2016. This is put on by the cltc.ucdavis.edu. That's California Lighting Technology Center. Great resource for all things lighting, lighting technology, lighting controls, understanding the code. I go there often, or I go to their website often with questions. I think it's a great resource in lighting. It's not so challenging in residential, and in commercial it's very challenging. So it's the Lighting Technology Center is a great resource, just as Energy Code ACE is, and for the rest of it, and maybe lighting too. But the energy code ACE I go to for other reasons, almost everything but lighting. Anyway, that's my spiel on them. Major changes to the lighting code. So now all lighting, all lighting changes are mandatory. Lighting is not part of the energy budget, so there's no trade-offs. You can't say, well, I want to put incandescents in, but I'm going to build bigger walls. That doesn't happen. These are all requirements. Some of those requirements are they have to be high efficacy. And what they've also done is they've relaxed the requirement on luminaires, which is the fixture type, and with a more focus on the lamp. What that means is we can now screw in light bulbs once again according to the energy code. And a whole bunch of how many does it take to screw in a light bulb jokes are now viable, and future generations can enjoy them as well. But so screw in light bulbs are okay everywhere in this code except for in can lights and ceiling recessed can light fixtures. For can lights, they have to be either pin-based or an integral. Really, it's going to be an LED, integral LED system, which I think I've got a picture coming up here for to show you some. But it's just where the whole fixture itself is one kind of piece of sealed device that has an LED in it. But everything else can be screw-based, but there are a few limitations on it. Sources that qualify as high efficacy: linear fluorescent lights, pin-based CFLs, high-pressure sodium metal halide, and induction. Other lighting, basically this means that the LED lighting will be, all LED lighting is allowed as long as it meets the JA8 requirements. That's Joint Appendix 8. JA8 are the requirements, and here's just a few of the JA8 requirements so you get a taste for it. These JA8 requirements were put in ostensibly due to the fact of when like CFLs came to the market, they were the new thing. What was that, 10 years ago or something? They came out and there was kind of quality suffered on some of the early CFLs, and then there was a lot of take back in the market, and CFLs didn't gain adoption as quick as they'd like. So these JA8 requirements are an attempt to make sure that the quality of LED bulbs are high enough that they last long enough that people will buy them and will use them. But there's an efficacy requirement here: color rendering index, color temperature, dimming. The two probably most important, and it is fairly challenging to go buy a light bulb these days because there's so many options. But the color rendering index of at least 90 out of 100, and the color temperature. Just real quick, I'll say that there's two main color temperatures of LEDs: 2700 Kelvin and 3000 Kelvin. 3000 is a brighter light. And brighter light is not what you always want. The 2700 is a cooler light. It's more of a calming light. You want that in rooms where you're going to be relaxing, like your living room, your bedroom. 3000 is a brighter, kind of makes you more alert. You want that in rooms like your kitchen, or maybe your office, where you're never going to be relaxing, like you want to be on. So just buy them accordingly. But having the right bulb in the right location in the house is really important for overall satisfaction of the LED bulbs. The other thing down here, labeling. So every screw-based LED that is JA8 compliant will have a marking on it that says will be stamped JA8-2016 or JA8 2016-E. That -E means that that bulb is rated for an enclosed fixture. So that is a fixture that is enclosed and has slightly higher temperatures. And from my understanding, that's why LED bulbs, screw-in bulbs, are not allowed in can lights, is that they're concerned about the elevated temperature in that can light that's often puncturing the ceiling and in the hot attic. So And so your downlighting requirements, like I said, they still have to be high efficacy. They cannot be screw-based sockets. They do have to be JA compliant. These pictures on the right are all integral LED downlights. The one on the bottom and the far right, I just took a picture of those at ResNet last week, and that's an LED. Essentially, it's an LED can light, but LEDs are such now that you no longer need a can. So that little knob that sticks up on the back of the LED right here, these are the same light. This little knob right here would just kind of fit up into the J box, and it would make this whole fixture look like a can light, but not be a can light. The thickness here is like ½ an inch. So can lights are certainly changing. The technology is, but the code as well. And then the electrical box requirements. So for new construction residential, a lot of times there'll be blank electrical boxes left in the ceiling, and that's so that when the homeowner moves in, they can like buy a ceiling fan and put it in themselves. The code made it so that you can only have this equivalent number of blank electrical boxes as you have bedrooms in the house. Doesn't mean they have to be in the bedroom, but you can only have the same number of blank J boxes in the ceiling or above 5 feet from the floor. Usually that's going to be the ceiling, right? And those blank J boxes have to be controlled by either a dimmer, a vacancy sensor, or a fan speed control. So they understand what will be going in there. And then control requirements. Have changed. So all of these lighting changes means that there's no more wattage counts. You don't have to have half the wattage in the kitchen be incandescent and half high efficacy. The wattage counts are gone. Some of the controls have stayed. So bathrooms, laundry rooms, garages, utility rooms, they all still need at least one luminaire or fixture on a occupancy sensor, or a vacancy sensor. Those are two different animals, a vacancy sensor. If you install a JA compliant screw-based, it still has to have a dimmer or vacancy sensor wherever it's at, except for hallways and closets. Yeah, seems like there was something else I wanted to say there, but I can't think about it. All right, we'll go on. And then outdoor lighting. Outdoor lighting also has to be all high efficacy. The real change here, the real difference here is that not only does it have to be high efficacy, but you cannot be able to turn it on during the day. So those bullet points there are all basically different strategies to make sure that you can't power on the light source outside. There will be a manual on-off switch so you can turn it on, but there'll be some other control on it that knows that it's not dark out and it won't power the light. So that's going to be, you could do it with a photocell with motion sensor, photocell time switch, astronomical clock, and energy management system. Lots of different ways to do it. But even if you flip the switch on, it will not turn the light on until it's dark outside. That's the basic requirement for outdoor lighting. And again, this is lighting attached to the building because that's where the code stops, is attached to the building. And that's it. And if there's any questions, we can answer that now. Hopefully there's a question or two.
We do have one, and then while everyone else is asking them, we can go over this one. Do the lighting requirements apply to retrofit and remodels as well?
It's yes and no. Certainly yes, in terms of all bulbs are all lamps are gonna have to be high efficacy. Typically yes, they do, because they don't require complex control changes, and they are going to be triggered. But I would certainly consult with the building department that you're working in and verify how they want to verify compliance on additions and alterations.
Okay. Is there a threshold of project cost or similar that triggers the changes?
No, not that I know of.
Okay. We had a question about the code being effective in multifamily as well. I believe that's a yes, right?
Yes, yeah. The multifamily changed the same date, and so did commercial. Multifamily is a little bit different in the high performance attics, A and B, are typically not an option. The prescriptive assumption in multifamily is that the ducts are already in conditioned space. The wall requirements are the same as what we've shown here, where they've gone up in thickness and R value. And again, those are going up again in 2019 as well, walls and attics. But multifamily followed in line with what I explained here today for single family.
All right. I don't have any other questions as of right now, so I just wanted to let everyone know if you were unable to ask a question or anything else pops in your head after the webinar, you can send them our way at the rnc@trcsolutions.com email address. I'll also be sending a follow-up email to all attendees, so you could reply to that as well.
Great. Well, thank you, everyone. Glad you made it. And let us know if you have any questions.